Hi everyone, my name is Aryan Soma, and this is my presentation on the challenges of hypersonic travel. Purpose and research question. The question I aim to answer is how can effective thermal protection systems be designed to manage the extreme heat generated during hypersonic travel? As a young boy, me and my mom would binge aviation documentaries together, and what I found most interesting in these documentaries was the SR-71, the closest plane to reaching hypersonic speeds. And these documentaries would spark my interest in learning about hypersonic travel. This map here shows the problem that I aim to solve. So as you can see, this is a culmination of all the flights that take place on Thanksgiving 2018. So in this picture, there's thousands of flights, and there's massive amounts of air congestion. Reaching hypersonic speeds would prevent that because planes would spend a lower amount of time in the air because they reach their destination quicker. So because they spend lower time in the air, there's less planes in the air at one time. So what is hypersonic travel? Hypersonic travel refers to velocities that are 5 times higher or more than the speed of sound. At sea level, a single Mach is equal to the speed of sound. So 1 Mach is equal to 767 miles per hour, 5 Mach is equal to 3,835 miles per hour, and 10 Mach is equal to 7,670 miles per hour. So hypersonic speeds are 5 Mach and above. So they are 3,835 miles per hour and above. On the left, we see a map, and in the map, there's a flight path for a Boeing 737 from New York to London. This flight would generally take 7 hours, but a hypersonic plane could complete this journey in 2 hours. So what challenges are associated with hypersonic speeds? Hypersonic speeds generate extremely high temperatures that put the technology and passengers on board at risk of failure and death respectively. The friction generated between the air molecules surrounding the plane and the surface of the plane generates heat that can cause material degradation. At hypersonic speeds, this friction can cause extreme temperatures. On the right, we see a chart, and this chart goes over the Mach numbers and their estimated correlating temperatures. So as Mach numbers increase, the temperatures increase exponentially. And as these temperatures increase, the risk is also increased exponentially. So what solutions are there to combat the extreme heats generated by hypersonic vehicles? The main one is thermal protection systems. To counter the extreme heats generated, hypersonic vehicles have thermal protection systems. These systems vary, however, their main differences are if they are active, semi-passive, or passive. Active TPS use actively controlled mechanisms or systems to manage the thermal environment. Semi-passive TPS generally requires some level of control or activation, but heavily relies on the inherent properties of the materials or simple mechanisms. Passive TPS relies solely on the properties of the materials to dissipate heat without the need of active control. So this chart shows different types of TPS and where they're all categorized. So we have passive TPS, which includes insulated structures, heat sink structures, and hot structures. And we have semi-passive TPS, which includes heat pipes and ablation. And we have active TPS, which includes convective cooling and film cooling and transpiration cooling. So in passive TPS, we see that it requires low to negligible energy because there are no parts that require a lot of energy, so energy consumption is pretty low. In passive TPS, there are parts that still need energy. However, we can see that it's still moderate. However, ablation is an outlier because what happens with ablation is as the heat hits the material slowly degrades away, and it's still considered passive TPS while not needing energy exactly. Active TPS requires high amounts of energy because it has parts that need a lot of energy to still work. Let's talk about some material and design considerations. So materials must have high melting points, low thermal conductivity, and good thermal shock resistance. Some examples include ceramic tiles and ablative materials. So ceramic tiles were used on the space shuttle, and they're known for their low conductivity and their high melting point. Ablative materials are materials that erode away in a controlled manner to absorb the heat. Designing the vehicle shape to minimize heat loads and distribute heat more evenly will enable a more efficient TPS. Two examples of this include blunt bodies and heat sinks. Blunt bodies, as in the Apollo command module, create a shock wave that keeps high temperatures away from the vehicle surface, and heat sinks, as used in hypersonic vehicles now, absorb the heat and radiate it away. Moving on to costs and environmental impacts. So there's high initial costs due to extensive research, testing, and material development that needs to be done. To date, NASA spent $10.6 billion developing the space shuttles, which are the only hypersonic vehicles today. And to develop commercial hypersonic vehicles, we would need to spend far more money. Hypersonic vehicles also require regular inspection, maintenance, and the replacement of worn materials. Inspections occur every flight for hypersonic vehicles compared to inspections every 1 year for commercial planes. Inspections are also far more in-depth, as hypersonic vehicles have technology far more complicated and advanced than in commercial planes. Hypersonic vehicles require extremely large amounts of fuel that can pose negative effects to the environment. The Concorde, the closest commercial plane to hypersonic speeds, burned approximately 6,771 gallons of fuel per hour. Hypersonic planes would need far more fuel because they reach even higher speeds. In conclusion, as I discussed in slide 2, my passion for hypersonic speeds started when I binged documentaries about aviation with my mom. In this project, I learned so much. However, the most important include thermal challenges of hypersonic speeds, how different types of TPS prevent excessive heat, examples of TPS, options of materials and designs that can be used, and costs and environmental impacts. While there are no hypersonic passenger planes now, multiple companies are working towards developing them. The development of effective thermal protection systems is crucial for managing the extreme heat generated during hypersonic travel. Thank you everyone for watching my presentation on the challenges of hypersonic travel, and thank you for giving me the opportunity to present.